Yang Zhenling, who talk about the use of vector potential in Maxwell's electromagnetism. Okay, the vector potential is the so-called gauge theory. Okay, who Yang Zhenling is a great contributor, so he chose that topic, understandably. And the reason that we have rather few such talks is not that we do not value the history of science or history of physics. Many great scientists appreciate the history of science, history of physics greatly. For example, more than 15 years ago, this famous Nobel laureate, Steven Weinberg, published an article in the journal Nature called Four Golden Lessons. One of which is that he advised young students of science to learn something about the history of science, or at a minimum, the history of your own branch of science. So the reason that we do not have many such talks is that we cannot find many such experts on this kind of topics here in Taiwan. So when I heard that a world expert on this subject is in Taiwan, we grabbed the opportunity to invite him over to give us a talk. So the speaker today is Jed Buckworth, Professor Jed Buckworth. Let me briefly introduce him to you. Let me move here so I can see clearly. Okay. Professor Buckworth is Reed Dreyfus Professor of History at Caltech since 2001. He is the director of the new Caltech Huntington Research Institute for the History of Science and Technology. I wish at some time in the future, Taida can also have such an institute. And he was the founding director of the Dibner Institute for the History of Science and Technology, and the Bernd Dibner Professor of the History of Science at MIT, before he moved to Caltech, I suppose. And he was awarded a 5-year MacArthur Fellowship in 1995. I suppose this is the famous Genius Award, okay? And so now you know that the Genius Award can also be awarded to a historian of science. And Professor Buckworth received his Bachelor of Science degree at Princeton, and he studied under the famous Thomas Kuhn. I suppose you have heard of Thomas Kuhn, this famous physicist turned historian of science, Kuhn. And for his PhD thesis, he has studied with Erwin Hilbert and Bernard Cohen. And he has published many papers. And his work has concentrated on the technical and philosophical content of scientific practice in physics, and on 17th to 19th century understanding of ancient astronomy, chronology, and writing. And recently, his interests include Egyptian hieroglyphs, that is 象形文字. Okay, the first time I learned of this word. So his topic today will be using Maxwell's equation before the electron. Professor Buckworth.
Thank you so much. It's a real pleasure to be here. I originally decided to come here because one of my former students who got his degree here, Chen-Tai Yang, got his PhD at MIT years ago, and he's a great historian of science now at University of Toronto. And we're working together. And then I was invited to give some talks, and it's been a tremendous pleasure. I've never been to Taiwan before. So today, on the advice of Chen Pang, when I was asked, I'm going to talk about how Maxwell's equations were constructed and how they were used before they became what you think of as Maxwell's equations, because the entire structure is completely different from what we think of today. I'm not going to spend much time on discussing issues of gauge invariance, although that is in fact a critical element in Maxwell's work, because almost all of the equations that he developed, including the ones for propagation, are propagation equations for the vector potential. And therefore he had to make some decisions about what in retrospect we call gauge. But rather I'm going to talk about how the equations were structured, what the foundation of them was, and what novel effects were developed in the years after Maxwell died to use these things to try and explain them, all in a world in which no microphysical conceptions whatsoever are being used. Maxwell's structure is based entirely on a continuum theory, a continuum theory which uses extensive parameters for what we now call permeability, dielectric capacity, as though they were completely continuous structures. I can tell you later on, if you want, how he thinks they may vary with the presence of material bodies. And that leads to a very different way of structuring physics. So here are some of the protagonists that worked in and around Maxwell's work. You have Maxwell up here, Richard Tetley Glazebrook, who was the head eventually of the first National Institute board for setting the values of various constants. John Henry Poynting, that's when he's much older. I'm sure you all know of Poynting's theorem. Joseph Larmor, a great exponent of Maxwell's work. George Francis Fitzgerald from Ireland. J.J. Thomson, of course, who first measured the charge to mass ratio of the electron. Henry Rowland in America, the very odd engineer Oliver Heaviside. And then some of the discoverers and further developers. Carl Hall, discoverer of the Hall effect. John Henry Carr, probably the single most important effect that could not be explained by Maxwellian theory. Peter Zeeman, the discoverer of the Zeeman effect, but who worked on other aspects of electrodynamics before that. And then two of the greats at the end of the 19th century, Paul Drude and Henrik Anton Lorentz. And you've heard, I'm sure, of many of these people. So let me begin by showing you how this works. I'm afraid I'm going to be technical about it, and you can ask me questions about how it works. This is a compendium of a subset of the equations as developed by Maxwell and presented by him in the treatise. I said I'm not talking about gauge, but I will tell you that he always assumes that the vector potential has zero divergence. He does not, nevertheless, use a gauge argument for this. I can discuss that later if you want. The Faraday effect then is represented in this fashion here. The usual relationships between induction and forces. The current, the sum of what we call the conduction current and the displacement current. The Ampere law. Now, one critical point that I want to make for you is this. Here is Maxwell's expression for what he called the electrokinetic energy of the field. And must remember, everything is continuous here. There are no discontinuities anywhere. This is expressed here as the scalar product of the potential and the current. Now, the fact is that Maxwell's current J includes the sum of the conduction and displacement currents. Both of them are present there. And that is critical for understanding some of the, in retrospect, complex difficulties of Maxwellian electrodynamics. And then the energies of the field expressed in terms of the inductions and forces derivatively, in this case, from this is the more fundamental expression as far as Maxwell is concerned, which also produced some problems later on. Let me now explain some of the key assumptions. There's Maxwell again. He died rather young, by the way, at 48, stomach cancer in 1879. Three basic assumptions. First, there are three continuous parameters which characterize all electromagnetic processes: permittivity, magnetic permeability, and electric conductivity. Let me just quickly say that the Achilles heel, the defect that they could never get beyond, and you'll see why in a moment, in Maxwell's continuum theory was the existence of conductivity. Loosely, as you'll see in a moment, because it dissipates energy. And this entire structure of continuum theory is based on energy structures, which I'll show you about in a moment. All electric currents, I'll show you how, are actually displacement currents. I'll show you how that emerges. These things are conservative in dielectrics and dissipative in conductors. And finally, and this is very important, the field equations are derivative of field energies. Heaviside had a different view of that. He was not educated at Maxwell. Heaviside was not educated at Cambridge, as most of the others were. And the point about this is that if you play around with the field energies, you get different Maxwell equations. And that's the structure of what these investigators did. When you have a new phenomenon, you don't just take Maxwell's equations and apply them, because there is no microphysics to work with. What you do is you alter the expressions for the field energies and see, and I'll show you how that works in a moment, if you can generate novel replacements for what we now call the Faraday, Ampere laws, and so on. Now here is typical example. You can find this in Maxwell's Treatise on Electricity and Magnetism, published in 1873. So let's say we have a capacitor and an interface across which, let's just make it simple, the conductivity and the dielectric capacity change abruptly. Then you have these relationships, very simple, within this region over here, and integrating them, since the total current is zero here, including both conduction and displacement. For that, you have decay of charge on the interface. Now, the general notion here that Maxwellians use is that what we now think of as conduction charge does not exist independently. It is entirely possible for there to be literally no charge at all in the universe. What happens is that scattered around the continuum are places where the ratio of conductivity to capacity changes. You have gradients. And at those regions, depending on the magnitude of the ratio, what we now call conduction charge appears. So for example, if you have a region in which the ratio of sigma to epsilon is comparatively small, it, from a human perspective, can look like this charge persists for a long time. In fact, Maxwellians think that in conductors, which have very high conductivity, they have vastly higher dielectric capacity, so that you can get decays in the right way. Now, one of the most important effects that was involved in the construction of field theory was the discovery by Faraday, Michael Faraday, in 1845, of what I'm sure you all know as the Faraday effect, namely the rotation of the plane of polarization when passed through a suitable liquid under a magnetic field. It was a stunning discovery and very surprising for the following reason. Optical rotation of polarized light by this time is well known. I should say that the wave theory of light itself is only about 20 years old by this time, but it had developed very rapidly. And it was known, for instance, that if you pass linearly polarized light through a quartz crystal, along the axis in the right direction, the plane of polarization rotates, and then if you then reflect it back, the plane of polarization rotates back, as though it were moving along a screw. In the Faraday effect, of course, that's not what happens. If you reflect it back, the plane of polarization continues to rotate just in the same way it did as it was traveling through, which seemed to field theorists to indicate that there was a rotational motion of some kind going on in the field, which led to some speculations concerning the structure of the medium, the continuum that is carrying these things. I'll say some words about that later. Now, how did Maxwell handle this? Well, as I just said, the treatise is based on energy expressions, not fully developed by Maxwell, but more so by his followers later on. And at the end of the treatise, he decided to see what would happen if he played around with the energy expressions for the field by making two assumptions. One, that in the medium that carries electromagnetic processes, of which light is an example, there are motions. These are continuous motions. All these fields are continuous. And that this vector here would represent a distribution of velocity, with this being the physical displacement. And this, the omega, represents what I just mentioned a moment ago, this notion that there is a built-in rotational structure, a vorticity in the field. Thinking about it, Maxwell came up, I don't know exactly how he did that because we don't have the manuscripts, with the following speculation for what you should add to the usual continuum kinetic energy of a fluid to see what would happen. Now, what did he then do with this? What he did was he ran it through Lagrange's equations, suitably modified for a continuum, which wasn't an easy modification at the time, to deduce the corresponding wave equations. This was the result, and indeed it generates exactly the correct behavior for the Faraday effect. That equation actually does very nicely govern the Faraday effect. You can see the usual terms for propagation here, and these added terms here, which produce the requisite directed rotation. Now, all subsequent equations for this effect, including the ones developed later by Larmor and Lorentz, have this general form. Of course, they don't get it in the same way. Now, and I will now be relating all of this to novel effects. New discovery, 1875. Maxwell's still alive. He died in 79. In Glasgow, in the laboratory of Lord Kelvin, a new discovery is made by this man here, John Carr. He, first of all, discovered that when glass is subject to electrostriction, that is, you put it in an electric field and it changes its form, that the result of that is that it becomes birefringent, just like any crystal, at different propagation velocities in different directions. He pursued this to see whether there were other possible effects, in particular ones maybe that had to do with magnetism. And in 1878, 3 years later, he discovered what is without doubt the single most complicated and difficult effect produced in the 19th century, the Carr effect, because it involves every single possible parameter in electrodynamics at the time. And that is, he discovered that linearly polarized light reflected from the surface of a metal placed in a magnetic field becomes very slightly elliptically polarized. And I mean very slightly. And a major part of the effect is that the major axis of the ellipse, showing it here, is rotated from the original polarization in a way that somehow depends, and he doesn't know how, he's not actually a mathematician, on the angle and plane of incidence and the direction of the magnetic field, as well as what metal you're using at the time. This is going to be very important. Very small effect. I'll show you how small in a moment because there's controversy over this. Now, as I say, this is the most significant discovery in optics between Faraday and the Zeeman effect.